Good morning, students. Today we will do the optical practical. The first today we will do from previous year question paper. Here we have taken the last year question paper 2017. See what we are going to do in this optical practical. This experiment determines the focal length of the given convex lens by no parallax method. So here this is a convex lens and we are going to calculate the focal length of this convex lens. And you are provided with an optical bench, and this is the optical bench. Okay, next thing, a lens holder. This is a lens holder. And next, a convex lens. This is a convex lens, and two optical pins. See here, this is the optical pin and here is another optical pin. So between these two optical pin, one that can be used as the object pin and another optical pin that will be used as the image pin, and the facing towards the optical bench, the left hand side pin that will be treated as the object pin, and the right hand side optical pin that will be treated as the image pin. Okay, and see, this is the optical bench, and one scale is given, and the graduation is here from 0 to, see here the initial reading is 0 and it is up to 150 centimeter, and facing towards the scale which is given on the optical bench, the left hand side pin that will be the object pin and right hand side pin that will be the image pin. Now according to the question paper we will do the experiment. First, see the procedure. Determine the approximate focal length f of the given convex lens by projecting the image of a distant object formed by the lens on a wall or a screen. So here, this is the given convex lens and we are going to calculate the approximate focal length by distant object method. So here we have taken the distant object as the tube light. Okay, and we are going to calculate the approximate focal length of this given convex lens. See, we are getting here the image of this tube light, and when you get the brightest image, and that will be the position of the focal point, then you have to measure the focal length, and we are trying to find out the focal length by the distant object method. And with the help of the scale we are getting here the brightest image, and the corresponding reading is 15.1, and this is the approximate focal length of this given convex lens. When you come to the lab, then you can easily do it. Okay, so the first part is completed here. The approximate focal length of the given convex lens is 15.1 centimeter. That you have to note down in the lab manual, and record the value of f in centimeter correct up to 1 decimal place. That means the value that will be in 1 dp. Next part, see in the procedure, arrange the object pin O, the image pin I and the lens L on the optical bench in figure 1 below. When you see the question paper, then according to the question paper you have to adjust. And here this is the object pin O and this is the lens L and this is the image pin I. Okay, where you will get the inverted image of this object. Okay, next thing, place the object pin O at the 0 centimeter mark. We have already placed at 0 centimeter mark. This is the object pin. According to the question paper, we have already placed the object pin at 0 centimeter mark. Now, and the lens at 70 centimeter. See, first we are keeping the lens at 70 centimeter. We are keeping the lens at 70 centimeter. See, at 70 centimeter we have placed the lens. Okay, next part, so that the object distance u that will be 70 centimeter. See, the object is at 0 centimeter and lens is at 70 centimeter. So the object distance from object to lens that will be 70 centimeter. Okay, next thing, look at the tip of the object pin O through the lens from a distance so that you see an inverted image of the object pin. In order to do this, we have to see the inverted image of the object pin here. We are moving in the forward direction and in the backward direction. What are you moving? We are moving the image pin in order to get the inverted image of the object here at this optical pin. Okay. Now we have to adjust the image so that we can remove the parallax. What do you mean by parallax and how we can remove the parallax here? Unless and until you are not getting the inverted image of that particular object pin at this point and point to point. See, here is the tip of this object pin, and when you get the inverted image, this tip has to come here, and then we can remove the parallax. So how we can do that? This inverted image may cross or it may move up this pin, so you have to use this screw to adjust the pin, okay? Or that inverted image can cross this pin on the right hand side or it can cross on the left hand side. Then you have to adjust with the help of the screw, and when you will be able to bring the inverted image at this point, at the point edge, then only the parallax can be removed. And after doing this, that means after removing the parallax, you have to note down the position of the image pin. I have already removed the parallax in this case when we have placed the object at 0 centimeter mark and lens is 70 centimeter, okay, and we are looking through the lens and we are getting the inverted image of the object pin at this point, and there is no parallax because we are removing and we are trying to remove and already have removed the parallax. When you are looking through from one side to other side, there is no variation. Always we are getting the inverted image at this point edge. That means the parallax is removed. Now see the position is here 90 centimeter. The position is here 90 centimeter. So this is the position for the image pin at no parallax condition. That means the parallax is removed here. Now position of the lens is 70 centimeter and position of the image pin here is 90 centimeter. So if we want to calculate the image distance, then we have to subtract the reading of the lens position, which is at 70 centimeter. So image distance, that will be 90 centimeter minus 70 centimeter, that will be 20 centimeter. Clear? Now repeat the experiment for 4 more values of u, that is 60 centimeter, 50 centimeter, 40 centimeter and 30 centimeter. This is given in the question paper. Now in order to do this, you have to bring the lens at 60 centimeter so that the object distance that can be 60 centimeter. Why? Now object is fixed at 0 centimeter. You are bringing the lens at 60 centimeter. When you are bringing the lens at 60 centimeter, then the object distance, that will be 60 minus 0, that will be 60 centimeter. The same procedure, you have to adjust the position of the image so that you can get the inverted image of this object pin at this point, and you have to adjust to remove the parallax. And after removing the parallax, you have to note down the position of the image pin. Then you have to calculate the image distance. Okay. Then for the third observation, for 40 centimeter, you have to follow the same procedure. Then for the 30 centimeter, you have to follow the same procedure. And after doing this, you have to do some calculation, which is given in the question paper for each value of u. That means for 70 centimeter, for 60 centimeter, for 60 centimeter, then for 50 centimeter, then for 40 centimeter, then for 30 centimeter, you have to calculate x value. Then y value. What is x? X equal to u plus v by 100. This is given in question paper. Then y value uv by 10. Okay. And tabulate all 5 sets of u, v, x and y with their proper unit. In the last year, we have done this practical, and I am showing here one experimental value that I have done in the lab. See, we have taken here 70 centimeter object distance, and v value we got here 19.3, and x value what we are getting here, x equal to u plus v by 100, and after calculation we are getting here 0.893, and y value u into v divided by 10, this value is 113.5.1. Okay, then for 60 we are getting different values, for 50 we are getting different values, then for 40 we are getting different values, next for 30 we are getting different values. That means we have to put all the values in the table. Okay, now in the question paper, see, plot a graph of y versus x. What is y? You have already calculated. Y value, this equal to uv by 10. This value you have to plot along this axis. And x value u plus v by 100 along this axis in 2 mm graph paper. Always you have to write their scale division 1 SSD. Smallest scale division. Suppose you have taken an initial reading 0 and next reading 10, and in between 0 and 10, 10 division. So one smallest division, that will be 1. I am not telling about the unit. When you are plotting here, then you must write here the SSD. 1 SSD along this axis is equal to numerical value and then corresponding unit you must write here. Okay, and when you put the values after doing the practical, then you will get a straight line, and you have to draw the best fit line, and after drawing the best fit line you have to calculate the slope, because it is given in the question paper, calculate its slope m using change in y divided by change in x. So you have plotted here y along this axis and you have plotted x along this axis. So if we consider two unknown point after drawing the straight line, then this will be two non-experimental point, because we did not get this one from the experimental observation, and after drawing this best fit line we are considering this point and this point. Okay, so you have to consider these two non-experimental point, and considering these two non-experimental point we have to calculate delta x or change in x and delta y or change in y. Then you can easily calculate the slope m, and after that, and this value that will be in three significant figures. See, in the last year we have done this and is coming here 150. Next part, find f using f this equal to m by 10, and we have done here f this equal to m by 10. What we got here, m value this equal to 150, so 150 by 10 is equal to 15 centimeter. Okay, that means the focal length of this convex lens, that will be 15 here, and if you do the experiment clearly, then this value and the approximate focal length value, that will be same here. In the first case, when you have done here the approximate, when you have calculated the approximate focal length, which I got here 15.1 centimeter, and from this practical we got here 15 centimeters, so more or less same here. So my suggestion, when you will calculate the approximate focal length, you should calculate accurately and you should do the practical clearly, then both the result, that will be same. Okay, thank you all.